Can everyone hear me now? Can people online hear me? Great. Okay. No, save as presented slideshow. Cool. Okay. Thank you, everyone, for coming. I'm going to talk about our recent paper that we've submitted to ITP a couple of weeks ago about how we're creating end-to-end verified systems that of verified systems that contain neural network components and some of the infrastructure we've built in order to support that. This is joint work with Luca and Wen and Bob from Strathclyde and Katya. So, okay, everyone knows that. We're here, we're not going to talk about that. This is an internal talk. Okay, motivation. So, let's take an example. We have a car traveling along a road. It's an autonomous vehicle. It's controlled by a computer. It's traveling in the X direction, in the horizontal direction along. We're going to ignore horizontal movement for the purposes of this being an example. But it does have a strong, unpredictable crosswind blowing across the road. It has the car has a y velocity for how its position on the road is changing in the y direction. It can use sensors to detect where on the road it is, but these sensors are noisy, so it may not give it a perfectly accurate reading. And the goal of the controller is to try and keep the car on the road, so not go beyond 3 or -3 in the diagram. And I mean, for the purposes of this talk, we're just going to examine this problem, but realistically, it would be keep the car on the road while optimizing for a complex series of other goals concurrently. So the more realistic example would have many other goals that the controller was also trying to do at the same time. So, well, we want to formally prove that our system never goes off the road. We don't just want to test it. So we can try and formalize this. We can try and formalize this in Agda. We're going to discretize the state space and split it up into discrete points in time and discrete simulation of it. Obviously, better to do it continuous, but for the moment, we're going to do it discrete. So we're going to formalize the state at each point in time is the current wind speed in the y direction, the true position of the car on the road, its velocity in the y direction, so how fast it's moving up or down the road, and the last sensor reading that it took. So that's its position plus some amount of noise. The observation, and each observation, we're going to assume an oracle that gives us the observables in the simulation, and each observation has how much the wind is changing at that point in time, so a delta on the wind, and how much error is on the current sensor reading. I should say that this is an open talk, so if people have questions at any point, please do just interrupt rather than wait till the end. Cool. And we're going to assume that we have some sort of controller that takes in 2 rational numbers and returns another rational number. So for the purposes of this, the controller is going to take in the current sensor reading, so where the car thinks it's on the road at the moment, and where the previous sensor reading, so where it thought it was on the road previously. So that tells it, is it shifting up or shifting down, and by how much. And as an output, it's going to give us a change in velocity. So how much should I counteract? How much should I drive? In which direction should I drive to counteract the drift? So we can use these things to formalize evolution of simulation. We have an initial state where everything starts off to be zeroed. I mean, you could initialize it to be non-zero. That's not important, but just for simplicity. We then have a next state function that takes in the observation at the current point in time and the current state and produces a new state. So the new wind speed is simply the old wind speed plus the observed wind shift. The new position of the car is the old position of the car plus its velocity plus the current wind speed plus the new wind speed that's just been calculated. Its new sensor reading is the new position plus whatever sensor error was observed, and the velocity is the old velocity plus whatever the controller is telling us to do. So, and then we can create the final state of the simulation by simply iterating next state over repeatedly from the initial state over a list of observations. So what would we like to prove about this system? Well, let's take this one and we'll say that assuming the wind can shift by no more than 1 unit per unit time, and that the sensor is off by no more than 0.25 units, then we would like for the car never to leave the road, no matter what series of observations or wind shifts or sensor errors we get. So that's the safety property that we would like to prove of the system. And again, we can formalize this where we can say, okay, well, an observation is valid if the sensor error is less than 0.25 and the wind shift is less than equal to 1. And the car is on the road if the position in the state is, the absolute value of position is less than equal to 3. And the desired theorem that we would like to prove is this, that for any sequence of valid observations, you're always on the road in the final state. Everyone happy with this formalization of the system? Okay, so you can prove this inductively by forming the right inductive hypothesis about your states based on the previous state. And it requires a bit of moderately heavy-duty algebraic manipulation in order to prove it. But the proof boils down to you need this result to hold about this controller, the implementation of which we had not specified yet. So it says that, well, X is the current sensor reading, Y is a previous sensor reading, but it says if the current and previous sensor reading is less than equal to 3.25, then the absolute value of the output of the controller plus 2 times the current sensor reading minus previous sensor reading is strictly less than 1.25. I'm not going to go through the details of deriving that. You're just going to have to trust me on that one. It's not very interesting deriving it. But so this is what we'd like to hold for the controller. So we have this abstract controller and we have this property that we need to hold of the controller. But the challenge is that, okay, now we want to implement this controller with a neural network. And disclaimer, maybe this isn't, as it stands, it's not a very interesting problem to solve with a neural network, but if you added more concurrent optimization steps as things to optimize for, then it perhaps would be a real problem that you'd actually use a neural network for. Indeed, there's a Nature paper that's received a lot of press in the last week or so where they claim to have used a neural network to beat top video game players in Gran Turismo video games where they race these sorts of cars. So yeah, they do use neural networks for these sorts of controllers. What are the difficulties in trying to formalize this neural network and these properties of these neural networks in this proof of systems? I mean, neural networks in general are massive. The state-of-the-art ones in NLP and vision are 600 billion nodes. And just the representation of the network is 10 gigabytes in size. That's just the weights. So I'm not claiming that we're going to be verifying those anytime soon, but the state of the art is enormous. And people really use these huge neural networks. So just representing them in your theorem prover is challenging. There are no discrete subcomponents of neural networks that carry out semantically meaningful tasks. You can't isolate, usually, unless you have a very special neural network architecture, non-standard neural network architecture, you can't point to this part of the neural network and say this part of the neural network is responsible for solving problem X. And this is how you build up proofs in interactive theorem provers. Traditionally, you build it up top down. So in general, it's utterly infeasible to represent the neural network and do it in Agda and create this proof. The neural network that we have that uses this controller, we've built a massive one. It's utterly overkill, but it's 20,000 nodes. If you try and represent this 20,000 node neural network in Agda, Agda is going to crash. It's not even going to type check. It's just too big. So luckily, we don't have to prove it in Agda. In the last 5-6 years, there has been a lot of work on coming up with special purpose tools, automatic theorem provers, for proving properties about neural networks. And the motivation for this was this very famous example of adversarial attacks, where if you add small noise to very clear examples for that neural networks trying to classify, then the noise fools the neural network. It's like a visual illusion from a neural network, and the neural network will give a completely wrong answer, even though previously it's very confident, and just tiny imperceptible changes result in erroneous classifications. This property was called robustness, and basically the property that you're interested in these neural networks to have is that small changes to your input space should only result in very small changes to your output space. It shouldn't, adding a little bit of noise shouldn't completely throw off your classification result. Neural network, they're well known not to be robust using standard training methods. Almost all neural networks are vulnerable to these attacks when they're trained using standard methods. And people have shown that these attacks really happen in the real world, and you can really add things to stop signs for self-driving cars, and it will misclassify it as a 70-mile-an-hour sign. So it's a real problem. So they built these verifiers, this verifier technology, to try and solve this problem, to try and prove robustness of neural networks. What hasn't received a lot of work been done on is actually using these verifiers to prove larger systems, large properties of larger systems, like the example I've just shown. Traditionally, they verify that the neural network is robust, and then that's it, job done. They don't tend to show how properties of neural networks lead into being able to verify properties of larger systems. There's a whole range of domain-specific verifiers exist based on different technology. Marabou is a big one of the first ones. It's based on SMT technology, basically represents a neural network as a massive SMT problem, but exploits the symmetry and the structure of the neural network in order to get a lot of speed up, hundreds or thousands of times the speed up over traditional SMT solvers. Another big one is ERAN, which uses abstract interpretation plus mixed integer linear programming solvers. Can prove properties that talk about, well, this region in the input space gets mapped to that region in the output space. Does that region in the output space contain any counterexamples to your property? There's verisig that uses interval arithmetic. There's a whole bunch. We chose Marabou as a target because it is complete. So it's guaranteed to give you a yes or no answer. If it says, the other ones, ERAN and verisig, because they're based on over approximations, they're more performant, but they may say, I don't know whether the property is true or not. And Marabou is more expressive as well. It can solve a larger range of properties than ERAN, and as we're interested in general properties rather than robustness, Marabou seems to be the one to go for. So, what is Marabou? Well, as I said, it's basically an SMT solver. If you have a query that involves a property that involves a series of networks, here the property references the property that you want to solve and verify for the neural network involves the neural network F being applied twice. So there's two copies of network F, and there's network G as well. And you label each of the inputs using consecutive x's, x variables, and you label the outputs as y variables. And you then write a query that relates the x variables to the y variables. And Marabou will tell you, does there exist a assignment to the x's such that the relationship for the y's holds, such that all the relationships that you specified holds. So it's a satisfaction problem. So let's go back to what we wanted to prove about our controller. And here are the equivalent Marabou queries. So because we've got an absolute value, we convert that into a disjunction of properties. So the first query on the left says that, okay, well, if our our inputs are in the right range, then the output of the controller plus 2 times the current sensor reading plus the, that's negated, yes. Yeah, minus the controller minus 2 times the current sensor reading plus the previous sensor reading is greater or equal to 1.25. And query 2 is, okay, again, that's the other side of the equation. It's saying if you negate the left-hand side, and that's greater than 1.25. So this is if Marabou can find a series of x values that create a y that violates this, then we know that the property can't hold, property can't be true. If it can find no satisfying assignment, then we know that the universal property stated above is true. Questions? Okay. So, how we verify the property holds of a neural network is now solved. We'll use Marabou. How do we integrate this into Agda is the question. How do we connect these two parts up? Well, traditional SMT solvers have been integrated into theorem provers for at least the last 10, 15 years, if not before. Yeah, almost certainly before. Anyway, can we use the same pattern? Well, the problem is there's various problems actually that come with neural network verifiers that don't occur or do occur or may occur to similar extents or not quite the same extent, but don't apply to SMT solvers. So the first one is that we would like to model the function in Agda. We would like to model the network in Agda as a function, right? You apply the network to some input, produces some output. But the Marabou queries we've just shown is modeling the neural network as a relation between its inputs and its outputs. So there's that disconnect between the two models. Scalability. We still can't represent the neural network itself in Agda. The networks are still going to be too big to do so. Maintainability. The networks are going to get retrained. Most neural networks get retrained frequently as more data comes in. The model, even if you could represent it in Agda, right? The model in Agda is not going to be the canonical one that you deploy on your system. So if you retrain your neural network, you want somehow your proof in Agda to notice that, right? But at the same time, we've said we can't represent it in Agda. So there's some issues there. The next one is performance. Verification of neural networks is very expensive. I mean, big SMT solver, when you chuck huge SMT problems at SMT solvers, you sometimes have this problem as well. But neural networks really are almost guaranteed to be massive SMT problems, and they may take minutes, hours, even days for the verifier to chew through. If you're doing this in an interactive theorem prover whose interaction mode relies on you regularly rechecking your proof locally, you really don't want to be calling out to the verifier to re-verify your problem every time you hit type check for your verifier. So we've somehow got to decouple the verification, the actual verification of the network from the ITP checking system. And finally, the specification should be reusable, right? The specification needs to be used in many other parts of the neural network lifecycle. Verification is just a small part of constructing the neural network. You will, by default, if you train it just using data, it's very unlikely that your neural network this property will satisfy the specification for all inputs. It may, if the data does obey the specification, which you would hope, the training may get it so the neural network obeys it, 98% of the time. But that last 2% of the time can be very difficult to do, to get the neural network to satisfy just using data. So you somehow want to incorporate that specification into training as well. And there's things like lightweight falsification for these properties for neural networks that use counterexample search, that use derived gradients or loss functions from your specification, and use the gradient of the loss function to do intelligent search through the state space to find counterexamples, which isn't handled by these verifiers either. So what we would like to avoid is having to rewrite the specification many times in all these different tools. Writing it once in your ITP is unlikely to be the right answer because, they are general purpose programming languages, a lot of the modern ITPs, like Agda and Lean and stuff. Idris, you really don't want to be doing neural network training in your ITP. You don't want to have to implement your training algorithms or your gradient-based counterexample search in these ITPs. Okay, so what is our proposed solution to all these many problems is we have built a system called Vehicle. Don't quite ask me about the name. It's not specifically to do with this example that I've shown. The fact that we're reasoning about a vehicle has nothing to do with the name. It's more general than that. So what does the vehicle system look like? Well, the user writes a specification of what they would like to hold about their neural network once in a high-level functional programming language, specification language, which comes with the vehicle system. The user provides the neural network in a standard portable ONNX format. So that's widely used cross-platform training independent representation of neural networks. Vehicle will then take the high-level spec written in something that's hopefully readable by non-experts and compiles it down to Marabou queries. Marabou then takes the Marabou queries and the ONNX network and checks whether it holds. If it does hold, big if, but let's assume it does. If it does hold, then it comes back to Vehicle, which then writes out to a cache file that says, okay, this is the status of this proof. It's been shown to hold. It holds the cache file holds a hash of the neural network that was verified, so that it can detect later on if the neural network changes or gets retrained. It can, when it hits a cache, it will rehash the network to check that the network is still the same as it was when the original proof was verified. Vehicle will then generate an Agda file, which is an Agda version of the specification for the neural network. This is done automatically. The Agda specification does not call Marabou directly. It calls, when you type check the Agda specification, it will call back to Vehicle, which will then check the proof cache for the status of the proof. You can then build a larger formalization, larger proof of the system on top of your specification for the neural network that is automatically generated. And then that whole system can then be checked in Agda. Crucially, the neural network is not represented directly in Agda. The generated Agda specification is simply a black box function of the right type. Eventually, if we can port the ONNX bindings for running inference on the ONNX model, it should be 100% possible to call the ONNX network from Agda. We've already written Haskell bindings for the ONNX network, so that the vehicle compiler can run the network itself. But this is the proposed way that we decouple the proof of the neural network from the implementation of the network itself, maintain the black box abstraction. I mean, people always say that neural networks are black box components. From a perspective of your proof about the larger system, it should still be a black box component. And from the perspective, I mean, that's the philosophy of the vehicle system. But there's competing arguments. Katya has a very different view on it. I know we have some interesting discussions about it, but yeah, black box maintains the black box abstraction. Let us have a look at the actual generated vehicle spec. Is opening VS Code going to crash my computer when I have Zoom open at the same time? Is the question. Let's go no. Oh, yeah, so, okay, so let's have a look at the vehicle spec for this. Well, I've actually got this in. So this is the specification in the vehicle language. It's a dependently typed language. So although we have type synonyms, that's just to help our users who are probably going to be, yeah. I'm not sure why we've had a specific type synonyms. It was a user interface design that we decided on. Anyway, yes, type synonym for type synonyms. So we say that input vectors are tensors of rational size 2. We declare an abstract network called controller that takes an input vector and produces a rational. Notice there's no implementation provided. There's no reference to the network on disk. This is the network is passed to the compiler at a later stage. We have some projection functions out of the input tensor to give it some nice meaningful names. Take the exclamation mark is lookup, so takes the first component and the second component. We can assign meaningful names to the subparts of the query. So we say that the input is safe if, sorry, this should read current sensor between minus 2.5. Really, this should be called current sensor and previous sensor, not current position, previous position. So the preconditions of the property, and then we define what it means for the post conditions of property to hold. So if you apply the controller, then 2 times the current position minus the previous position has got to be less than minus 1.25, and sorry, greater than minus 1.25 and less than 1.25. And then we say that the controller is safe if for all x, safe input implies safe output. What is the corresponding Agda interface that this generates? It generates this thing. Oh, this is out of date. Okay. Anyway, ignore. I'm just going to delete that bit. Sorry, it no longer generates. Let's just call that evaluate. It generates corresponding definitions for every definition you've written. So input vectors, tensor rationals, length 2. The controller itself is, as I said, we haven't written bindings to evaluate the ONNX one. So in the latest version of this, it just generates a postulate. But eventually you should be able to write a macro that calls out to the ONNX file and just runs the ONNX file to evaluate it, so that you can actually evaluate this network in Agda itself. Generates corresponding projection functions, generates the conditions, the pre and post conditions, and then it generates a proof. It generates a term representing the final property that you're interested in. And this is implemented by a macro in Agda that simply calls back to the vehicle compiler. So using this, you can then import this module. So it provides, you can import this module, you can use controller in your larger development, you can use this proof safe in your larger development, and you can build your larger development on this. Yes. So to return to the presentation. This is the code that I've just shown you. So let's talk about a little bit more about the design of the vehicle language itself and some of the kind of non-standard transformations in the compiler that are needed for this domain-specific language. Vehicle is very much designed as a specification language. It's not designed for arbitrary computation. It doesn't support recursion or data types or type classes, which gets us out of a lot of implementing a lot of nasty things like productivity checkers or things like that. So it's quite cut down. We provide a series of built-ins that we think are useful, and we're willing to expand. We're willing to bet that we can, after an initial period of growth, that it will reach a fixed point, and that actually the number of built-ins is actually going to need to be limited, because after all, neural networks run on a very limited subset of data, right? They're computation about on numbers, and the verifiers themselves can only handle linear or semi-definite properties, relationships between the inputs and the outputs. So there's not much scope for doing. I mean, you might be able to formulate a property that you want, but the technology that vehicle relies on isn't going to be able to solve the problem anyway if it's too complicated. Some details about the internals. We implemented in Haskell. We weren't brave enough. There was a momentary debate about whether we should actually implement it in one of these theorem provers that tend to also be general programming languages. We weren't brave enough to do it in the end. There was a parser implemented by BNFC. For those who are interested in parsing technology, so we are running some limitations of it. We also want the generated interactive theorem proving code to be as close to the original user code as possible. So desugaring and resugaring is a problem because how compilers usually work is that you have a rich surface language. It takes the rich surface language and translates it down into a small core that is minimal, and then type checks that. The problem is that we've then got to be able to take the type check code and generate Agda or other interactive theorem proving interface that looks as close as possible as the user. So there's a big emphasis on reversibility of the sugaring and desugaring process needed. So there's a bit of bookkeeping, non-trivial bookkeeping there. Let's have a look at some of the compiler passes. So type checking, sorry, I should say type checking is done using dependently typed unification algorithm. There's type class resolution in there as well for our limited set of built-in type classes. After type checking, we then are going to try and compile to Marabou. So we're going to take our spec and try and generate those queries that I showed you earlier. Normalization is very much standard, apart from a few points where we also want to normalize quantifiers. So for instance, our property normalizes over these variables x, which are tensors of rational size 2. We obviously don't have any notion of a tensor or anything else, any other complicated data structures in Marabou, so we have to normalize these out. So you normalize it out as you would expect. Instead of quantifying over the tensor itself, you have to automatically translate the quantification of the tensor to the quantification over its members. And indeed, TensorFlow and vehicle handles arbitrary dimensional tensors as well. So it works for images. It's not just vectors. The next step after normalization is that we need to eliminate all the other constructs in the language that Marabou doesn't support. So for instance, if statements need to be normalized out to logic. Obviously, this is not a valid transformation all the time, right? Because your if statement might be in an arithmetic expression. So what you have to do is you have to lift your if expression to the top level. So you have to first lift the all ifs as high as you can in the expression till it reaches somewhere a point in the program where it's of Boolean type, and then you can perform the elimination. Obviously, there's a blow-up cost to this as well, which I'm going to talk about when we go to the next slide. So after eliminating if expressions, we turn universal quantifiers into existentials by negating if necessary, because if you remember, Marabou is a satisfaction, only can solve satisfaction problems. So you need to negate quantifiers, negate any properties that involve universal quantifiers, and try and prove the converse. And then you want to convert to disjunctive normal form to split up, because again, Marabou, these verifiers can't deal with disjunctions. So this is obviously problematic, right? Because disjunctive normal form can have an exponential blow up from the original one. Sadly, this is just an inherent feature in using the current generation of neural network verifiers, is that they do suffer this exponential blow up. This has a lot of problems. Causes a lot of problems in the robustness world when they're trying to prove robustness of classifiers, because you want to prove for every input X, then the neural network is going to produce the top ranked class out of all the classes that you can classify. And what is that? That's a universal property, so you negate it. So you say, okay, well, I want to find a counterexample such that there exists another class that is greater, but whose score is greater or equal to the true class. That gets converted into a disjunction, which is proportional to the length of the number of classes that you have. And suddenly you're performing, if you have 100 classes in your classifier, you're suddenly performing 100 robustness queries, each of which may take hours. Yeah, so yeah, problem, but one for future research for the verifiers themselves, I think. So what do we get at the end of this process? We get something like this. We say that there exists inputs, P0 and P1, such that blah, 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 the condition, or there exists these other ones, and the other side of the absolute value greater than 2.5 rather than less than equal to minus 1.25. We're just going to consider the top one for the process of continuing through the compilation. So let's revisit the model. Just a reminder of what we're trying to target. We are trying to target these magic variables x zeros, y zeros. It's very upsetting. The fact that they hard code, I mean, these names really are hard coded into almost every neural network verifier. The input formats are really appalling. So you actually have to come up with variables. You actually have to rename everything into this format and identify all your nice, meaningful named variables. You have to calculate the logical transformation into two of them. Wen has a personal crusade that she's going to try and come up with a new standard for this that is SMT-lib compliant as an SMT-lib theory that supports variable renaming and names, network-specific names and stuff. But we're a long way from there. And even if we do come up with something beautiful and shiny, we're unsure how much buy-in we did get from the community anyway. So they're very much research tools at the moment. They're not. Yes. Okay. So if normalization, we also have a problem before we do this transformation. We have a problem that we don't want to artificially blow up the problem. If normalization has resulted in the same neural network being applied to the same input in the property more than once during normalization, then we don't want to generate unnecessary input variables, because unnecessary copies of the network, because each copy of the network gets translated directly into an SMT problem. So you're going to have an exponential blow up in the complexity of your query when run through Marabou, if you don't be careful that you're not duplicating work. So to avoid this, we identify every application of the neural network to a input, and we lift it to the top level of the expression. So any duplication, if you're applying, controller to P0, P1 multiple times, it'll get lifted to a single instance of it. Yeah, common sub-expression elimination algorithm. This actually needs to be amazingly efficient because of the exponential blow-up in the previous form. Because we're in disjunction with normal form, you're going to have to perform a lot of these operations, and these queries can be really, really large. If you have a neural network, if you have an image vision neural network that takes every pixel as an individual input, you may have 784 or thousands of inputs to your neural network. So your queries may be thousands of lines long. The common sub-expression elimination algorithm needs to be efficient. We're not there yet. I mean, we tried the new Coda-Brown representation proposed by Connor and others 3-4 years ago. We haven't yet managed to get the performance that is promised out of. I mean, we've got a real language. I mean, in the papers, it's a toy language. There's various niggles that we're struggling with degrades performance. We think we're n squared, but I mean, it's it's claimed it's n log n. Yeah. Okay, but assume we can do that. We then take this expression down the bottom, and every time we find a let binding, we perform the following substitution to translate it into a relational model. So let's say we have some output y equals some network f applied to a tensor of inputs e1 to en, and it's being used in some expression e. What we do is we keep track of where we are in that sequence of networks in that diagram. So how many input variables we've assigned so far, how many output variables we've assigned so far. We equate the inputs to the neural network with the right set of magic output variables, and then conjunct it with the expression E with the output of the neural network substituted through for the series of magic output variables that, that the query format requires. Again, in general, this isn't a sound transformation because you may not be at type bool. You may not be at a Boolean, your expression may not be Boolean type, but we have our let lifting always lifts the network applications as high as it possibly can. So just under the quantifiers. So we're guaranteed to be a Boolean type, and therefore this transformation is type preserving. Okay, so let's have a look at this. So this is example at top, we have our let expression at top, and then at the bottom, we have this equating of the user specified variables or the transformations of what were the user specified variables to the magic variables that are required. And then the outputs. Yep.
We have two questions in the chat.
Yep, go for it.
Okay, so the first one was for the generated Agda looks similar to the vehicle specification. Why not use Agda as a host language for vehicle as an embedded DSL rather than vehicle as a standalone language?
So I think I covered, yeah. I think may have tried to cover that earlier, but maybe I didn't do a very good job of it. Basically, there's many other tasks that you would like to use the specification for. You would like to use it to generate loss functions, which generating TensorFlow code or PyTorch code. You'd like to use it for counterexample search, gradient-based counterexample search. Agda is not the right language in which to implement these things. I'm not saying that in future generations of languages, interactive theorem proving languages are going to be powerful enough in which to do that and easy enough to use, but they're not there yet, I don't think.
The second question is, your CSC example only has one instances of controller P031.
Yep.
To become the equal.
Yep. That is absolutely true. I'm sorry, I was talking about a hypothetical property. I should make that clearer, that contain multiple neural network, multiple instances of neural network. A classic example might be monotonicity. So you have a neural network that a regression neural network, and that you know it should be monotonic in one of its inputs. So you say, okay, for every two inputs, x1 and x2, such that every element of x1 is equal to x2 except the first element, which is greater or equal to the first element of the second input. Then if you apply the neural network to both of those inputs, then you want the output of the neural network applied to the first input to be greater or equal to the output of the neural network applied to the second input. So that would be an example of a property that uses two of the same neural networks applied to different inputs. An example of a property where you have multiple different neural networks in specification might be teacher-student models. So you train a really, really large, complicated neural network on a data set, and then you try and train a much smaller neural network to mimic that larger neural network as closely as possible. And you might want to verify that the output of the student network deviates by no more than epsilon from the output of the teacher network. So yeah, so in general, yeah, we do have to consider these slightly more complicated cases. Great question though, both of them. Okay, so yes, so we have this. Then we have to eliminate the user added variables. So as we introduce these equalities, perform these substitutions for the let bindings. We keep track of what equalities we've introduced. And as we traverse back up the expression, every time we hit an existential that has been made equivalent to a magic Marabou variable, then we substitute through for that user variable, the magic Marabou variable for the user variable, and then renormalize afterwards. And we get something that looks very much like a Marabou expression. There are some problems here. I mean, if you, for instance, if one of your neural networks was f applied to x plus 2, for example, rather than f of x, then you don't have a direct substitution you have to perform. You have to perform algebraic manipulation in order to get a solution for the user variable in terms of the magic variables. And in general, this may be arbitrary expressions, right? It's not just going to be linear, so you may not even be able to do that manipulation. We have ignored that. We throw an error if currently, if at the end of this process there are any user variables still left in the expression. Area for future research and, well, improvements. I'm not sure how. I haven't actually thought about it hard, so I'm not sure whether it's feasible to do in the general case, or whether we need to plug in some sort of SMT solver to solve or mixed integer linear programming problem to try and solve for the user variables in terms of the magic variables in general. So we're now almost there, and to finally convert to Marabou, we split the conjunctions into separate quotes. We need to check for linearity because Marabou only solves linear problems, so we throw errors if we have a non-linear expression at this point, and then we just convert directly to the slightly idiosyncratic Marabou syntax. Yeah, the Agda transformation is much simpler and much simpler, as you might imagine. I should say that there is nothing magical about Agda. I mean, we have used Agda because all 3 people who are doing the serious hacking on the project were familiar with Agda, and therefore it's a convenient target language, target interactive theorem prover. It's a really minimal transformation to Agda. It's 400 lines of Haskell code or something. It could very easily target Coq or Idris or any other interactive theorem prover, suitably expressive interactive theorem prover that you'd like. There's some more interesting targets out there actually than the traditional ones. I mean, I said at the start that we were doing a discrete simulation of the system. Really, you'd like a continuous model of the system and continuous guarantees. That's quite complicated to do in an interactive theorem prover, differential equations, stuff like that. There's a really cool, more recent one called Chimera X, which is 6-7 years ago by Andre Platzer's group in the States, which is an interactive theorem prover especially designed for different systems of differential equations, improving safety of controller systems. So that might be a very interesting next target to try and integrate with, and then we could have a verify the safety of continuous systems that use neural network controllers as well. Yeah, so conclusions. Well, it's possible to get guarantees about systems that involve neural networks. Oh, sorry, systems that involve neural networks. We went completely over the top, and as I said, we trained a 20,000 node neural network to do this, when in fact you can solve it with a 1 node neural network. For this toy example, this was mainly as a proof of concept to show that you could have a formal end-to-end proof involving such a large system. In the previous record that we found for this in interactive theorem provers is a 20-node neural networks. There's 2-3 papers in Coq and Agda, which, I mean, they had to directly represent the neural networks in these systems, but that's the largest proof that we've ever found involving a neural network was 20 nodes. So this is really hopefully this is really a step change towards building these larger systems that actually involve neural networks and being able to formally verify them end to end. Luke is going to hate me about this. I would just like to end on a kind of more philosophical problem, in that this is really cool stuff, there's a lot of there are applications to this. It's not clear to me personally, although other people disagree, that neural networks, that these systems are actually convincing in that you actually want a neural network in the position that it is in the system. That really you should have a classical controller in the center and neural network should be relegated to the outside. I mean, let's have a look at this diagram. I mean, these are the world's problems, and these are problems solvable with neural networks. One source of suitable problems for this sort of technology is that the problems are solvable by classical algorithms, but for some reason, either size or performance or other reasons, that you might want to solve with a neural network instead. So you have the specification of a neural network derived from the equivalent classical program that you're trying to emulate. So that's a source of problems. But more interestingly, there's these problems that we don't know how to solve, right? We don't know how to solve with classical algorithms, but we do know the properties of the desired solution. We know what a solution would look like, but we don't know how to find one. And some of those are amenable to being solved with neural networks. So we're also interested in these. My question is, where are these problems? It's really hard to come up with any. The neural network verification community, the people who build Marabou and Aran, have maybe 4 go-to examples total. There's robustness, there's monotonicity, there's hierarchical classification. So, you want, if you're trying to classify objects, you want it to be more likely that it's going to be either classified as a cat or a dog than a cat or a human. And there's a control system called ACAS-2, which is for autonomous aircraft that they verified using this. Again, I've never been quite convinced. I've never heard a super convincing reason why they need a neural network to do that. They claim that it's compression, but yeah, open to. And watermarking.
Yeah, remember the calculators example?
Oh, yes, and watermarking. So yes, they would like to have it so that people haven't stolen your neural networks. So you want an input, you want a special input that if you feed it to the input, produces a crazy answer or produces your name, say, or something. So something to prove that the neural network hasn't been, is yours and hasn't been retrained or stolen. Or if anyone has any ideas on why it's so hard to come up with such problems, because in theory, this intersection sounds like it should be quite large, right? I mean, problems that we don't know how to solve, but we know the solutions of, that seems like a big set. Why is the set of problems that we can actually find and use this technology on so small? So that's a question I'm going to end on. And then, yeah, it's a bit bibliography. So, yeah, thank you all for coming.
Another question.
Yep.
So is the linearity constraint of Marabou inherited by vehicle? What about in future when vehicle can target other solvers that don't suffer this constraint? Will the semantics of vehicle generalize away from linearity constraints? And should the expressivity of vehicle be constrained by the expressivity of its solver backends?
So can you just read the first sentence again?
So is the linearity constraint of Marabou inherited by vehicle?
Inherited by vehicle. So no, so you can write any expression you want in vehicle, allowable by the syntax. You can write deeply nonlinear expressions. It's just that it will error when you try and compile to Marabou specifically. So a very, very last stage of when you have actually targeted Marabou itself, you're actually converting to the Marabou syntax. Then it does this linearity check to check that you're actually, because we figure that we can give more usable, readable error messages than if we just chuck the property to Marabou, and Marabou complains about non-linearity. We can give much more meaningful ones. There are solvers out there that can solve semi-definite, semi-definite problems. So non-linear but semi-definite, slight step up. I haven't seen, again, the semi-definite examples. The examples of problems that they use for semi-definite ones are not terribly convincing about why you'd use a neural network to solve them. They have a single pendulum system. They have that recognizing if you do repeated image recognition on digit classification, that the sum of the errors over time is not going to exceed a certain threshold. Yeah. So yes, so vehicle is not limited by the backend. It is general. It's just the last stage of compilation checks. Cool. All right. Thank you very much.
Thanks for the talk.
Any questions? Any more questions?
I just have one question.
Yeah.
It's a quite probably naive question, but so traditionally when you get proof failure, you get a counterexample that then informs your design.
Yep.
In this kind of scenario, does it just really mean go back and retrain your network?
So
there's nothing you learn from the counterexample.
So there is nothing you. I mean, so depending on the verifier technology, some of the verifiers will give counterexamples, some of them won't. Yeah, the counterexamples don't tell you very much. I mean, they tell you that it's wrong in that particular region of the input space, and you can add it to your training data set, retrain, or you can add more, you can do data augmentation around that area if it's an example where you don't have very much data, or you can go out and get more data in that area. As I said, there are training algorithms that try and incorporate these specifications into the training procedure itself. And therefore try and not just optimize some data, but also optimize for its property. And they're kind of vital in order to get an actual verifiable end-to-end network. But yes, you're right. It doesn't give you any insight about why your neural network is falling over. Though there is work trying to do that, but it's not.
When you had the intersection on the right, I thought you were going to start to talk about things like drug therapies and system biology and that. Is that not an area where people are using neural networks like folding proteins and things? Which
Yes, do they have? Yeah, they might have. I mean, the big sort might be they need to have strict mathematical specifications of properties, right? Which, I mean, I haven't looked into it, so I don't know, but I haven't seen any work on that. The big one that I think might be a potential is that people are using neural networks to solve mathematical conjectures, trying to find counterexamples or in certain areas. That might be a richer source of examples, although obviously there's no larger proof of correctness of the whole system. You're just trying to ensure that your neural network obeys the mathematical laws that you must hold them essentially.
You mentioned earlier on your talk the fact that here you're working with one neural network, and then you might have a new version of the training. So right now you have one example with the size of the neural network. Do you actually already started working with examples of the variation of the same neural network retrains and trying to prove the same property, and how you go about it?
So if
same question.
Yeah, so if you retrain it, then obviously the system will say, if you try and retrain it and you try and check the validity of proof in Agda, Agda will call vehicle will say the proof doesn't hold, it won't go away and re-verify it automatically because you've said so in Agda. Agda will just say end up saying the proof's failed. Vehicle will then go away and have to recall Marabou on it. In general, there is a line of work on trying to do proof transference. So you have this big series of linear inequalities that hold about the internals of a neural network. You've tweaked your neural network slightly. Can you reuse those to drastically speed up re-verification if you've only made small changes to the neural network? There is work out there. There is no mainstream verifier that I know that incorporates such technology. It's very much a cutting edge research question about whether you can even do that. Yes.
Because do I understand it correctly that basically trust the proof like an oracle.
It's not trusted end-to-end verification. You're right.
It's just from the intent of proving.
It's yeah, maybe is end-to-end the wrong word? Maybe I'm using it. Would the CompCert people object to me?
Probably CompCert people
would object to me using the term end-to-end.
Is there any chance, like, I mean, because you say it's based on SMT servers,
Yeah.
right? And I mean, like,
Certificates.
SMT talk basically like replace proofs in SMT servers in talk, and so basically like this is what classical SMT and
Yeah.
SMT provers would do, and I wonder whether there's any thought on how you combine these, or whether this is completely unfeasible.
Wouldn't you run into efficiency issues?
That's what I wonder.
Yeah,
Like, I mean,
it's
I
like
think-
if you have
You are so inefficient, right? Because you replay the proofs. You don't. So I wonder whether it's even like infeasible to like basically like.
So the problem is that these systems don't produce proofs. The verifiers don't produce a proof. They just say whether or not they can find a counterexample. There's no certificates produced. There's no. So I completely understand what you mean. And indeed, it's deeply worrying because they ran a competition last year for these different verifiers. And they had maybe 20 verifiers compete, and they had 200 benchmarks. And 30% of the benchmarks had more than 2 verifiers give conflicting answers on either side of them. So, yeah, the integrity of the system is challenging. Yeah.
So if you would like, I don't know much about neural networks, so it's like, but I mean, like if you have, you said it was similar to SMT.
Yeah.
Could you basically have the problem like transform whatever get into set 3, for example, which gives
That indeed, that's exactly what the first back in 2016, that is basically what they did, was that they translated it directly into Z3.
but I mean, there you get a certificate.
You do get a certificate. Z3 also chokes when you go beyond 15 nodes. The problem is not the number of nodes as well, it's the non-linearity in the activation functions. The actual linear algebra combining of the values, easy. The activation functions are the things that kill you. Because even I mean, obviously you have all the non-linear transcendental functions out there, sigmoid, tan H, things like that. Even the most basic ones like rel-u, right, have a discontinuity and need to be split up into disjunctive cases in the SMT solver. So your disjunctions become proportional to the number of nodes in your network at a minimum, bare minimum, and as you plus all the, I mean, not completely non-trivial. I mean, moderately complicated linear algebra that also goes on in actually the layers themselves. So you quickly run into, if you're not doing domain specific things. But you're absolutely right. In theory, the same techniques used to produce certificates in Z3 should be transferable to things like Marabou, which is based on the same underlying technology. I know the Marabou group, the leader Marabou does say that they're working on this, but they've been saying that for a little while, and no papers have been produced. So. Yeah. Yes. If anyone has any examples that they know, I mean, I think I'm going to talk to. Yeah, there's some people who do some autonomous submarine work, right, in the department. But I am trying to try and track down and see if they have any counterexample, any use cases. If you know anyone who has any examples, please send them our way as well.
Even though it's not the ideal thing to be using on network, they are being used, so it's worth having the ability to verify them. Right?
Yes. So this is Luca's argument, is that these neural networks are being used in these positions for right or wrong, and therefore this is useful. The perfectionist in me squirms slightly at that, writing that, but yeah. Cool. Oh my God, I went way over. I'm really sorry. I apologize. Thanks again for the talk, and yeah. And next week it's Mara, right? Next week is Mara. There will also be an Agda reading group as well. Those who are interested in that.
Getting back to the Agda.